quantity. Let's talk about the quantity first. What is a quantity? Quantity, a quantity is some attribute of an object that you can imagine being measured. So in math, we deal with a lot of different types of quantity. And here's some examples of quantity. Height. Maybe your height is 6 foot, so it's a quantity. Weight, weight of any kind. Okay, let's say weight of a basketball, okay, which could vary depending on the size and what brand you buy. We can name that even weight as X. It's a varying quantity. It changes. Number of people in this class. We can name it as N. Age can be a quantity. Okay, it can be also N or X, T, or any variable. Or temperature. Maybe today's weather outside is 80 Fahrenheit. And angle measure is also a type of quantity. So it's important to understand what an angle is in this trigonometry class because in trig we deal with an angle measure as a quantity and anything that associated with angle measure. So we'll talk about what an angle is in a second, but I want to make it clear that angle measure is a type of quantity. And when we talk about quantity, there's two types of quantity: varying quantity versus fixed quantity. So varying quantity means it could change depending on the context of the problem or depending on what quantity we're looking at. Sometimes it varies. For example, number of people in this class could change depending on more people enrolling, more people withdrawing. Right? So it could be a varying quantity, or things like amount of cars I own. I only own one car, so for example, that will be a fixed quantity. So it's important to understand that there's a varying quantity, fixed quantity. And one thing to highlight is not all quantity is always fixed. Many times, a lot of quantities we deal with in math are varying. It changes. So let's talk about an angle. What is an angle? Okay, so we need to have a precise understanding of what an angle is before we go further. So an angle is the union of two rays having a common endpoint, which is also known as vertex. So in this picture, we have two rays, and these rays share a common endpoint called vertex. So it forms an angle. So right here, it forms an angle. Either this one or this one or this one, however we want to label it. Okay. Let me draw another one as an example. We can have two rays. When they share a vertex, it forms an angle. So in this case, we have an angle here, 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 and also here. Okay. So that's what an angle is. It's just literally union of two rays having a common endpoints. Maybe this doesn't seem like an endpoint; it seems like a middle point of the rays, right? So we can just also also think as just two rays going this forever, going this forever. Here's an angle. It form this. This is an angle. So angle measure, although we use the word angle and angle measure interchangeably a lot, for now it is important to understand what an angle measure is because the way we measure angle is very important and a big part of trigonometry. So angle measure is a quantity that measures this quote unquote openness. How do we measure this openness between angles to rays? Okay. So in this picture right here, we have a ray, again, ray, and a vertex. Here's angle. How do we measure this quantity? Okay. So that's the big discussion. One of the main point of this video, how do we measure this angle? Because angle measure is a quantity that we can measure. For example, if you have a length or height, which is a quantity, we can measure. We can measure using a ruler or tape measure and so forth. Weight, we can measure with a scale. Right? So how do we measure this quantity known as angle measure? Okay. And we'll talk about that in the next minute or so. But before we do that, let's clear one thing up about an angle. So here, two rays share a vertex, so it forms an angle. And for angle, oftentimes we use variable theta. So this notation is called theta. And yeah, sometimes we also use x, but we use theta. Maybe let's call this angle theta 1. The question is this angle theta 1 same as this angle right here? Let's call it actually theta 2. Sorry about that. So is theta 1 equal theta 2? The answer is yes. Okay. These two have their same angle. And it turns out wherever we draw this angle measure, wherever this is between these two rays, all these are same angle. Okay, so that makes angle actually very unique. And we'll talk more about this when we talk about how to measure angle. But just keep in mind that for now, we oftentimes use this notation theta. And yeah, sometimes we use x or t or any other letter you can imagine. But one important thing we need to understand about angle, it's oftentimes is the varying quantity, not always a fixed quantity. It changes. It's a varying quantity. Okay. So there are different units, two different units for measuring angles. One is known as radian. The other one is known as degrees. And we'll talk about each one of them separately. It is crucial. It is crucial that you understand what radian measurement is independently from degrees, vice versa. So what I'm saying here is that you need to understand what a radian measurement is without relying on degrees. You also need to understand what degree is without relying on radian measurement. So we need to understand what radian is, we need to understand what degree is without relying on each other. These are separate ideas, and we need to understand individually, independently from one another. Okay, so let's talk about radian first. Radian is actually what you're going to see most in math classes, and I'll tell you why after we talk about it all. But radian is mostly used in terms of mathematical settings. Okay, and so the question is, why do we call it radian? Where does this name come from? Okay, so well, it turns out the radian is related to. Let me write it right here. It's related to. Can you guess it? Related to radius. That's where this name comes from. That's why it's called radian. It's relating to radius. So here I'm just going to give a basic idea before we look at formal definition of radian. So for example, let's say I have a circle with a radius 10 centimeter. 10 centimeter. Okay. And let's say I have an angle, this angle right here. So I'll start from here. Let's think this radius also has a ray, another ray right here. So I form this angle. Okay, let's call this angle theta 1. Okay. And it turns out when this angle was created, we also form an arc length. Do you see this arc length right here? Follow this line, this arc length. And we use the verb subtended. This angle subtends this arc length. And let's say this arc length, we measured it, it was 20 centimeter. Do you see how this radius length is twice as the, excuse me, I'm sorry. Do you see how this arc length is twice as the radius length? That makes this angle 2 radian. 2 radian. Or 2, we can just write, let me write it all. 2 radian. Okay. a little above 2 centimeter. This is 2 radian. Because the arc length subtended by, or we can say created by, the angle is twice as much as the radius length. Let's look at another example. Let's have another angle start from here, same ray, look at the red, and maybe let's look at this angle. This angle, let's call this angle theta 2. And it turns out, let's say this arc length is 5 centimeter. Okay. And we can also think as we start from this point right here. We start from right here and we create an angle this way. We went this much arc length and we ended here, which creates this angle. So what angle is this theta 2? Well, do you see that how 5 centimeter is half of 10? So this means we have half radian. Okay. So it appears that radian is just comparing the arc length in relation to the radius length. And that's exactly what radian is. So let me informally write down, and we'll look at the formal definition in the next page. So radian is using a radius length. Radius length. Let me underline that, radius length, as a counting, quote unquote, counting unit for the subtended arc length. So for the first angle we saw, this theta 1, this angle right here, the arc length was twice as large. So I need 2 radius lengths to cover 1 radian, 2 radian. 1 radius length, 2 radius length. So you can kind of see that 1 radian will be somewhere here then. Right? Maybe that's not so precise. 1 radian will be maybe like somewhere here. So here to here will be about 10 centimeter. It's arced, right? This is 2 radian. So in radian, we're seeing how many radius length do we need to cover the arc length that's subtended by the angle. That's what radian is. And it's not always going to be whole numbers. As we can see, we saw half a radian. So let's look at the formal definition of what radian is, now that we are kind of introduced to the idea. And then we'll look at more examples of radian. So radian is a unit, again, is a unit measure. We don't say radian is angle. Right? Angle can be measured in radian. Let me give you a similar analogy here. We do not say length is kilometer. Right? We say length can be measured in kilometers. Right? Length can be measured in miles. We do not say we don't say miles is the length. Right? So radian is just one way to measure angle. Unit of angle measure where 1 radian corresponds to an angle that cuts off an arc length equal to the radius length of the corresponding circle center at the vertex of the angle. Or we can say 1 over 2 pi of a circle's circumference. Equivalently, 1 radian corresponds to rotation from initial side terminal angle of 1 over 2 pi of a completed rotation. I'll talk about this appearance of number 2 pi in a second, but let's look at this example again, these 2 pictures. Here I have a radius length. Right here, 1 radius, whatever the length is. It could be 5 centimeter, it could be 10 inches, a foot, 3 foot. As long as this radius length and this arc length is same, I have a 1 radian of an angle. So this angle is 1 radian, 1 radian. And this picture right here on the right, this picture here, We have a smaller circle, which results smaller radius length and smaller arc length. But still we have a 1 radian because this radius length, and this arc length is same. So this angle right here is 1 radian. 1 radian. 1 radian. You see that? Yeah, 1 radian. So radian, how do we essentially find the angle radian? Using radius and arc length. Radian turns out is just arc length divided by radius length. So we're just dividing, which means what's the division mean? Here's another way to think about division. Let's say just talk about in general what division is. One way we can understand division. Let's say I have 8 and I do 8 divided by 2. Here, one way we can think about this is we're seeing how many times 2 can go into this number 8. Right? How many times can 8 go into 2 times? Or it can go into 4 times. That's what we're doing here. We're seeing how many radius length can go into the arc length. Again, it's not always going to be a whole number. We have way more angles than just 1 radian, 2 radian. Okay, so we'll look at examples on the next page, more examples next page. But this is how we find radian. Arc length divided by radius length. How many radius length do I need to cover the created arc length? It could be 1 radian, it could be 1.1, 1.001, it could be 0.5 radian, 0.000006 radian. Just there are infinite number of options because the radian is a real number in a real number system. So let's look at more examples of angle radian. I want to emphasize this again. It is very important to understand what radian is independently from degrees. I know we haven't talked about degrees yet. Maybe you heard of angle degrees, but just know that it's very important to understand what radian is independently from degrees. It itself is a very important idea that connects to all other trig functions we're going to learn later on. So let's look at the picture A. We already saw this. 1 radian means that radius length and the arc length, sometimes we often use letter S to notate arc length. The arc length and the radius length are the same for the created subtended angle. So we have 1 radian here. This angle is 1 radian. 1 radian, that's what they're saying here. 2 radian means, just write it here, we have twice the arc length. Excuse me, twice the radius length. The radius length is r, whatever r is, the arc length is twice as big. So this is this angle right here. This angle here is 2 radian. 2 radian. 2 radian. So if you look at the third picture here, we have all the radians, well, whole number, let's say. This angle right here is 1 radian. Here to here is 2 radian. 3 means we need 3 radius length. 3 times the radius length. 4 times the radius length right here. 5 times the radius length. 6 times the radius length. So 6 radian is just short of a full revolution. So let me highlight this. We have 1 radian, 2 radian, 3, 4, 5, 6. And that's where the number pi comes from. Okay. So it turns out, let me write it right here, the full revolution is about 6.28 in its unending decimal radian, which is actually equivalent as this number called 2 times pi. We call it just 2 pi. So 2 pi is about 6.28, and it's unending decimal. That's the full revolution. So the circumference of a circle, or full rotation arc length, is 6.2, about 6.28 times as large as the radius length. That's always true for any circle. Equivalently, then, half a circle, or half revolution, is pi. 3.14 unending decimal. It goes forever. We decide to call this number pi. So that's where the number pi comes from. So let me demonstrate pi in this picture A again, right here. What is pi? Pi is, it turns out that if this radius length is r, this arc length is pi times 3.14 times as large as the radius length. We multiply this number by radius length. So if the radius is 1, this arc length is 3.14 ... or we call it pi. We call it pi. And so pi is essentially the angle for the half revolution, or half circle. 3.14, we call it radian, pi radian. And oftentimes for radian, we don't write any unit. It's implied. If you see, okay, angle equals 7, that's implied that 7 is radian. Radian is actually unitless measure, and I'll demonstrate it later on. So that's where pi comes from. Pi is just a ratio between the arc length, half arc length, and the radius. And we have another pi here, which makes 2 pi. So that's why full revolution is 2 pi. So before we look at more examples, it's very helpful to, if you kind of have an idea where 1, 2, 3, 4, 5, 6 radian is on the graph, on the x and y axis right here. 1 radian is about here. This angle is about 1 radian. 2 radian is about here. 3 radian is about here. 3 radian is just short of a half a circle. And from here, we have to go 1 more radius length to get 4 radian, go 1 more radius length, and 1 more to go 6 radian, which is just short of a full rotation. So let's look at more examples of angles measured in radian. We can measure angles in radian by counting, quote unquote, counting how many radius length we need to obtain the arc length. So this, we already talked about it. Let me just box it. Angle in radian is arc length divided by radius length. So this fraction we can think as a rate of change, just like speed. When we think about speed, we briefly, well, not briefly, I'll say, kind of lightly, let's talk about, how sometimes we talk about how speed is distance over time, although it's more the average speed. But speed, usually we compare the distance and time. So if I'm driving 60 miles per hour, I'm associating the length, the distance, miles, with time, hour. Arc length is similar in that way, where we're associating the arc length and radius length to find the angle in radian. Okay. So let's look at some of these examples. 2 pi radians is about 6.28 if you write in numbers with decimals. This is the circumference of a circle. Circumference is 2 pi. So circumference of a circle is 2 pi times as large as the circle's radius length. So that's true for any radius. Even if radius is 10 kilometer, then the circumference of a circle is 2 pi times the 10 kilometer. So it would be 20 pi kilometer. It would be the circumference length, the arc length of the whole circle. 2 radian. There's no pi here. 2 radians means arc length subtended by the angle is 2 times as large as a circle's length. And we already saw 2 radian earlier. If this is the radius length, I have maybe about here 1 radian, and another arc length maybe about here 2 radian. I know it's not easy to compare the arc length and the straight line length, but just approximately this is about 2 radian. Half radian means the arc length attempted by the angle is half times as large as the circle's length. So if this is the radius length, think as I'm using half as the arc length. I'm going to arc it this way, and here's the half. This is half length of radius, whatever the radius length is. So let's look at some problems together. If arc length is 15 feet and radius is 70 feet, what is the measure of the angle in radians? So although we don't need to draw a picture to get this problem, let's just draw it so we can have visual. So here's 7 feet radius, and we draw maybe 7 foot in arc length is maybe something like this, 7 foot. Draw another 7 foot. There's 2 radian. Now 7 and 7 is 14, right? So we have to go one more. 1 foot. So we're essentially finding this angle. What is this in radian? Okay. Then we need to go back to this idea that radian is arc length divided by radius length. Well, arc length is 15 feet right here, given 15 feet. Divided by radius is 7 feet. You see that feet cancel out? We have 15 over 17. So we can just call it 15 over 17 radian. We can also write in decimals, which is about 2.14 radian. I'm writing radian right next to numbers right now because we're just learning what radian is. But oftentimes we don't use, you see many times where radian is not written next to number. If it's just given as an angle, hey, here's an angle 2.14, usually it's implied it's radian. Example 2. If the angle theta is 1.3 radian and the radius is 3 inches, what is the arc length? So we use this idea again. So let me write it again. It tells us that arc length divided by radius length equals 1.3. Well, what we want to find is the radius length. Let's call radius length S, variable S. We don't know what that is. So we know that S divided by radius length given as 3 equals 1.3. So we isolate this variable by multiplying 3 both sides. So then we get S equals 1.3 multiplied by 3 gives us 3.9 inches. So arc length is 3.9 inches. So in terms of angle, just to have a visual, if this is 1.3, oops, not 1.3, I'm sorry, 3 inches, arc length is a little bigger than 1 radian, it's 1.3, so maybe it's somewhere here. This is the angle, 1.3 radian. And this arc length is 3.9 inches. Okay, example 3. What is the angle measure of the angle below in radians? What is this angle? Again, all these are in radians. When real number is given without any unit next to it, it's usually assumed as radian. So here we're approximating, because this is multiple choice, is 120 degree, excuse me, 120 radian, pi, 2, 1, pi over 2. So let's eliminate. It's definitely not 120, because 120 radian means that if we have the radius length, let's say this is the radius length, then this arc length has to be 120 times bigger than the radius length. Definitely not, right? We can tell. So this is not it. If it's 120, we have to have this 1, 2, 3. We have to do this 120 times. It's not pi, because pi will be half a circle, half revolution. It's not 2, because 2 will be somewhere here. It'll be 1. It's about 1. This length look about 1 radius, right? Pi over 2. Pi over 2, which is about 3.14 divided by 2, is bigger than 1. Right? It's bigger than 1 radian. And we'll actually see what exactly pi over 2 is, but I can show you right now. If this half circle is pi, right? If I have this pi, is actually right here. Pi over 2 is this angle right here. So this angle right here, we also actually call this angle as right angle. So right angle is pi over 2. So this is the idea of radian. So before we move on, make sure to understand what radian is by itself without relying on degrees. So now we're going to look at degrees. Degree is also just a unit measure of angle in which 1 degree corresponds to cutting off 1 over 360 of a circle circumference within the angle's range. Equivalently, 1 degree corresponds to rotation from initial to the terminal side of 1 over 360 of a complete rotation. So what degree is that we have a circle, and at some point in time in history, the humanity or someone decide that we're going to slice a full circle into equal 360 pieces or slices. So here's the one slice, and that is 1 degree. And we have 360 of those in a full rotation. So where does number 360 come from? It's an arbitrary number that humanity decide upon. And there's many theories why we chose 360, because we could have chose 400. We could have defined the full rotation as 400 degrees. But why we chose 360? There are many theories on why. It's divisible by many numbers. It's close to number 365, which is how many days in a year. But regardless, that's the number we stuck with. Not that we need to know exactly why we chose 360. 360 is the number we chose there. And we know what? We're going to slice up the entire circle to 360 pieces, 360 slices. And one slice is 1 degree. If I have 9 of those, I have 9 degrees. If I have 12 of those, I have 12 degrees. Okay. And we can also think in this rotation. So if I have, for example, 90 degrees, 90 over 360 gives us, let me put degree sign, 1 over 4, which is 1 over 4 of rotation. So 90 degree means is 1/4 of rotation. So right angle, as we just saw on the previous page, you know how right angle is 1/4 of a rotation, full rotation, or 1/4 of a revolution. Similarly, we can do 180 degree, which is divided by 360, it gives us half a rotation. So 180 degree is half a rotation. So full rotation, half a rotation is right here. So this is half a rotation. So this is 180 degree. And for any angles, right, it doesn't have to be here. Numbers somewhat divide nicely to a fraction. But if we do 101 degree over 360, it's not going to be a nice fraction, right? But still, we can talk we can think about in terms of rotation. That's what degree is. Okay, so 90 degrees. Then we can also have half of 90 degrees. If this is 90 degree, half of 90 degree, 45, so this is 45 degrees. So there's one degree is very small, right? We have 30 of those, will be somewhere here. We have 60 of those, will be somewhere here. So that's the idea of degrees. Okay. So you can think as full circle is 360 slices for rotation, 360 degrees. And half of that is 180, half of that is 90, half of that is 45. Those are the major angles. And there are more major angles, like 30, 40, excuse me, 30, 45, 60, 90, 192. But for now, since we're just introducing what degree, know that how these are calculated. And one important thing about degree, it comes with this notation, degree notation, like I've been writing here. It's a tiny open circle on the right corner. Okay, so for degrees, either they have to say word degrees, or it has to have this notation to show that we're dealing with the angles in degrees. Okay. So let's talk about position of angles. So these are more of the convention that in math where in math class we're dealing with is one of those rules that we're going to follow. And of course, this applies to both radian and degrees. Remember, radian and degrees are measurement. So counterclockwise rotation is considered positive in terms of x and y coordinate, and clockwise is rotation is considered negative. So let's look at this picture. We have an initial side, and we start from there. We create this angle. This arc length is created, right? This seems like about what radian? What do you think? I'll say a little bigger than 2 radian, okay? And terminal side is the terminal ray. So now we label the initial side and terminal side. So initial side is always here, alongside the x-axis on the right side of 0, 0. This is always initial side. Terminal side is depending where the angle ends. That's what the word terminal means, right? Terminal means ending. So because this went to counterclockwise, this is a positive angle. A positive angle. Oops, forgot I. Positive angle. So how would the negative angle look like? So start from here. If we go this way, clockwise, we have a negative angle. So maybe I have an angle that ends right here. This will be a negative angle. A negative angle. And it can be measured in either radian or degrees. It can be negative 2 radian, or it can be negative 50 or negative 100 degrees. So then you'll see a number negative in front of, excuse me, you'll see a sign negative in front of the number. Coterminal angles. So coterminal angle is also important characteristic of angle. It is actually one of the very unique characteristic of angles. So we call it coterminal angle. Co means they share. I don't know if you heard terms like co-chair, or he and I are co-chairs to this committee. That means we both are chair, right? So coterminal share. They share. What do they share? Terminal sides. So it means share the terminal side. So angles that share terminal sides. And it turns out there are infinite of them. For each angle, there are infinite number of coterminal angles. So let's look at some examples. So let's look at degrees first. 140 degree. So this is positive since there's no negative sign from it. Here's the initial side, and it went to positive direction, positive angle, counterclockwise, and it ended here. So it's 140 degree. Equivalently, we can start from here and we go negative direction, negative 220 degree, it ends here. So 140 degree and negative 22 degrees are coterminal to each other. Or we can say 140 degree has a coterminal angle of negative 220. Or negative 220 degree has coterminal angle of 140 degree. So they share coterminal. We do not say those are same angles. That's different. So keep that in mind. Coterminal, the way we speak, we talk about angles are very important. Coterminal does not mean same. It literally only means they have a same initial and terminal sides. But that doesn't mean they're exactly equal angle. You know why? This is why radian is so important. Because in terms of the arc length it traveled, it's different. Okay? So amount of rotation, yes, they start at the same place and they ended at the same place. But the amount of the arc length they had to travel is different. So that's why now we don't call it quote unquote the same angle. They're coterminal angles. So let's look at the picture on the right. Here, again, initial side is same. This is the initial side. For 3 pi over 4, and understand 3 pi over 4 is harder for us to imagine what 3 pi over 4 is. If that's too difficult, we can always do this. Well, 3 times 3.14 over 4, because pi is about 3.14. Well, that's about 9 some decimal over 4, which is a little bigger than 2 point something, because 9 is bigger than 8, so 4 can go into 9, little more than 2 times. So this angle is a little bigger than essentially 2 radian, just to have a reference point. So here's 2 radian. It positive angle, it ended right here. Right? But let's look at this 19 pi over 4, which is just much bigger number than 3 pi over 4. Right? It's 6 times bigger, a little bigger than 6 times, right? Because 3 times 6 give us 18, and 18 is smaller than 19, right? But they start at the same side, initial side, and end at the same side. But what happens 19 pi over 4? Well, it rotates, right? Rotates once, rotates twice, rotates 3 times. So you can think as, yeah, we can follow this line. But essentially, what's happening, if I had to draw it here, we start from here, we rotate once, twice, 3 times, and come here and end up here. So these two angles are coterminal to each other. They're not the same angle. They have the same initial and terminal sides, but the arc length they travel is different. That's why we call it coterminal. This terminology is very important. We need to be precise when we describe angles. So these are the visual of coterminal angles. But then how do you actually compute coterminal angles, a given number? Because it's not efficient to always draw angles every time when we need to find the coterminal angles, right? So you can find coterminal angles by adding, You can find coterminal angles by adding or subtracting full revolution, multiples of essentially 360 degrees or 2 pi, depending on what unit measure is being used. So example 4, find the coterminal angles in 0 to 2 pi. So let's talk about the 0 to 2 pi first. Why is this important? Well, this is important because this is essentially saying find in this full rotation 0 to full rotation. Sorry, that's not the best circle, but 2 pi. So we want to look at essentially angle between 0 and 2 pi. Well, first we need to recognize that 25 pi over 4 is bigger than 2 pi. Because if I do the common denominator of 2 pi for 4, will be 8 pi over 4, right? Well, 8 pi is smaller than 25 pi, right? So this means that this angle right here contains more than one full revolution. So what we do is we start subtracting, we start showing work here, 25 pi over 4. We subtract 2 pi. We're subtracting full revolution. Well, we need to have a common denominator when we subtract fractions, right? Well, 2 pi, common denominator for 4 will be 8 pi over 4. It gives us 17 pi over 4. So when you come here, we need to check, is this in this range, 0 and 2 pi, is between these two numbers? If not, we have to subtract one more time. Or we need to subtract as many as we needed until we get an angle between these two ranges. Because each angle has infinite number of coterminal angle, we only want to find one that is between this range right now. So this is technically coterminal to this angle. But this angle right here is bigger than 2 pi. Because as we saw, it has to be smaller than 8 pi over 4. Right? Because 8 pi over 4 is same as 2 pi, right? So we have to subtract again. So let me erase this again to have room. So 17 pi over 4 minus 8 pi over 4. It will give us 9 pi over 4. Again, 9 pi over 4 is bigger than 8 pi over 4. So let me just erase this to have more room. So again, from 9 pi over 4, I subtract 8 pi over 4, which gives me pi over 4. So pi over 4 is in this range. It's bigger than 0, it's smaller than 2 pi. It's actually 1/4 of pi. So where's 1/4 of pi? This here is 2 pi over 2. Half of that is right here. The angle half of the right angle is the pi over 4. This angle right here. This is pi over 4. But then what is this angle? Just as a practice. Well, that angle actually, we subtracted how many times? We subtracted full rotation once, twice, 3 times. That means 3 revolution is added to this angle for 25 pi over 4. So if I were to draw it, here's pi. I mean, this is not part of this problem. We already found it. This is the answer. We're done. But I'm just showing so we can have a better understanding of what the radian and coterminal angle is. So here's the pi over 4. From here, we add 1, 2, 3. Now we have this angle that is 25 pi over 4. They're coterminal, so they start at the same place right here. They end at the same place. But 25 pi over 4 is way more arc length. Example 5. Find the angle coterminal to negative 51 degrees. Do you see the degree sign? So this is degree now. In this range, it's between 0 and 360 degrees. That means we're just looking at full revolution in just one circle. Now here we have to notice that negative 51 degrees is smaller than this number, right? That means we need to add so that we can bring this angles in this two range. So if I do negative 51 degree, add a full rotation, it gives me 309 degrees. So 309 degrees is in this range. It's bigger than 0, smaller than 360 degrees. So how does this look in picture? Well, negative 51 degree is maybe somewhere go this direction, negative. This is negative 51 degree. Whereas positive 360 degree, positive 309 degree is this. Again, these have same initial side and same terminal side. So they're coterminal angles. But the arc length they travel is different. But they're coterminal. Coterminal, the shared terminal. So like I said, it is important to understand like I said, it is important to understand what radian is conceptually independent from degrees and vice versa. But we still need to be able to convert one measure to another. This is similar to how we convert, for example, centimeter to inches or inches to centimeter, or miles to centimeter, or feet to miles, miles to feet. That's what we're doing here essentially. Okay. So convert, let's look at an example. Convert 3 pi over 4 to degrees. So we start with 3 pi over 4, and we need to multiply And here we're going to multiply 180 degrees divided by pi. And let me explain what this is. Here, essentially, we're multiplying by half a circle over half a circle. So this is essentially 1. We're multiplying by 1, which means we're not changing the amount of quantity. We're only changing the unit of measure, which means we're changing how it looks. So remember how half a rotation, this is pi, but this is also 180 degrees. So this is essentially, we're multiplying by the quantity of 1. Okay. And why 180 degree in the top? This is so that we can end up with the degree symbol in the end. So if I do this, pi cancels out. I have 3 times 180 divided by 4. Well, let's reduce some. 4 can divide by 2. 180 can be divided by 2 also. Oops, it's 90, not 98. 90. 2 can go into 45 times. So we have 3 times 45 in degrees, which is 135 degrees. That's the final answer. 135 degrees is the equivalent to 3 pi over 4. They're same. One in radian, one in degree. Just like we convert pound to ounce, for example. Right? So let's convert 225 degrees to radians. So here we have a similar idea, 225 degrees multiplied by, now we need to have 180 degrees in the bottom and pi in the top. The reason is because we want to cancel out the degree symbols. So when we don't have degree symbol, like I said many times, is imply radian. So then we have 225 pi over 180. Let's simplify. Both of them can be divided by 5, right? So it would be 45 pi, 5. Let's see how many 5 can go into 180. 3 times 36. And 5 times 9 is 45. 4 times 9 is 36. So it's 5 pi over 4. So 225 degree. 225 degree is same thing as 5 pi over 4. So one last thing I want to talk about is, again, the unit measure of radian and degree. So it's important to pay attention to the degree symbol. So if I have 3 degree, is vastly different from 3 radian. So if I say that theta is 3 degree, theta is 3, they're totally different angles. 3 degrees is very small relatively. 3 degrees is like somewhere here. We have 3 of those small slices, 3 degree. 3 radian, in the other hand, we know that if this is the radius length, we have 1, 2, 3, almost pi. They're totally different, right? So the way we recognize if the angle is in degrees or radian is solely on this symbol. If this is there, it's degree. If it's not there, it's radian. Or sometimes you see that it's written as or 3 degrees. That's also okay. So it's very important to write units when you use degrees. Otherwise, we'll assume it's radian. And one common mistake that can be observed is that Seeing pi itself does not make this is the radian. Okay? So technically, it's possible to have pi degree. Pi degree would be slightly bigger than this one right here. This is about 3.14 dot 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 degrees, which is again very small, about something like this. So do not just run pi. Just because if you see pi right away, it does not make it radian. It makes it radian when the says angle is given and when you don't see the degree symbol, because radian is mathematically uh, actually is more conventional. Degree is kind of, as a human, okay, let's decide 360 degrees, 360 pieces. Radian actually has a mathematical reason of comparing arc length created by the angle with the radius length. Okay? And as we learn more about trigonometry function, which is dealing with angles and some other distance, other quantities, I'll explain why radian is more used in mathematical setting.